All right. Anyone? Not yet? Okay, let's see what Piazza says. No. What? So far, no students willing to join office hours. Maybe it's a good sign, maybe not. 10:15. Ten. No. Hello.
Hello.
Go ahead.
So I posted a question on Piazza and I'm still a little confused by the response. It was for practice 3, question 28.
Just a second. Did I respond or someone else responded?
So you and one of the TAs responded. But one of the responses is no longer there.
Okay, I'll check what is the energy and joules. Over photon. All right, so 10. No. Another. Yes. Oops. All right, it's just easier if you guide me to the problem. Which problem did you say?
It's practice 3.
Practice. Where's here? Practice 3, number
28.
28. Well, now we've got time. So, was your number 199? Hydrogen?
Mercury.
Oh, mercury. Sorry. Yeah, Hg, mercury. And did you post your solution as well?
Yes, I did.
And how many neutrons was used in your solution?
So I did 119 neutrons, 80 protons, and 80 electrons.
I believe I saw 199.
I put that as the atomic mass.
But it was multiplied by the mass of a neutron.
No, so I have 80 times the mass of a proton plus 80 times the mass of an electron plus 119 times the mass of a neutron, subtracted mass of an atomic from that, and then multiplied the whole thing by 931.5.
And what did you use for atomic mass?
199.
So you had hydrogen, mercury 199,
Mhm.
and first let's check periodic table. There's mercury, mercury, mercury. 80. 80. So, oh, sorry, 80. Yes. So we've got this way. So 119. All right. And what values did you use for mass of a proton, neutron?
I use the ones on equation sheet 3. Would you like me to read them out?
Okay, so calculate and that's the conversion factor. So you need over 199 per nucleon, 80 times plus 80 times for electron plus 119 for neutrons and minus, well, 199, that's my natural instinct, times 91.5. Okay, so please read me the mass for a proton. 1.00.
7276. 1.007276.
I don't think, okay. You're using the equation sheet for exam solving web assigned problems.
Yes.
Why?
What do you mean?
Well, there's exam problems, there are web assigned problems. You're using data which required kind of or offered or suggested for the exams, but let me check, I don't recognize this. But for the web assign, I think it was here. Web assign may use slightly different values for the same, because it's web assign, it's not an exam.
So the mass of a proton, neutron, and electron for web assigned problems may be slightly different depending on estimation than for what we would use for an exam.
Maybe. And I mentioned that at the beginning of the class. I just want to make sure what values do we have in my slides. Okay, so I want to use those. 7276, right? You said. Come on. 7276, right? For a neutron, 008664, 1.00. Oh, those are electrons here. Neutrons are 0.8664.
It's 1.008664.
1.008664. And for the electrons, we have 0.000 54858. 54858.
Okay, my setup was the same, so I'm assuming it's just because of the masses that my answers are slightly different than the web assigned answers.
Could have been. Normally that's the case.
And then, do you also mind? So I put this on WebAssign, but it hasn't received an answer yet.
What do you mean? On Piazza, you mean?
Yeah, sorry, on Piazza.
Okay.
Do you also mind going for question 30 of the same set?
Yes. Okay. This is this. 28, 29, 30, 30. Complete reaction. Okay, that's a reaction. You may probably have a different reaction. Yeah.
Yeah.
Okay, you can just read your reaction.
So my reaction was actually not correct. So if it's electron capture, what decay would that align with? Because I initially thought beta plus.
If it's captured, it means it was traveling before the reaction happened, and then collided, and then that nucleus kind of absorbed it for a moment, and then decayed into something else.
Okay, so we would do oxygen.
So you have an oxygen. What specific? This is 8.
Oxygen 15.
15. And you said an electron was captured.
Yes.
So an electron.
Are you writing on the screen?
Yeah.
Just because I can't see anything.
Is it blurry?
No, it's just blank, like it's just a white screen.
That's strange. Just a second. Did you see it before what I was writing?
Okay, now you're clear. Okay.
Ah. Do you see it?
Yes, thank you.
Okay, thank you. Yeah, so
we want the charge to be the same on both sides, so 8 minus 1.
what's on another side?
So we know we're going to have that, I'm not really sure what it's called, but that V-looking one.
Neutrino.
Yeah.
Yeah, we'll ignore it, so don't worry about it. Where else?
But we also know that we need the element that has a charge of, or an atomic number of 8 minus 1, so 7. So we're going to have nitrogen.
So on the right side, it doesn't give you anything. You just have to figure it out.
So we have to write the entire equation.
Okay, could you please read the problem again?
Yes, write the complete reaction equation for electron capture by oxygen 15.
That's it.
Yes.
Okay. So 15 and 7, that should provide the nitrogen.
So for the exam, would we be given like the equation and just asked to figure out what the element is, or would we be asked to write the entire equation?
For the exam, there would be one unknown element
Okay.
in any type of a possible reaction. If the reaction would have been given or asked about, that reaction would have one unknown element.
Okay.
Because
and then
otherwise we wouldn't be able to figure it out.
okay, and then the only non-element parts of the equation that have charges are beta plus, beta minus, and an electron, right? For all types of decay.
Beta minus has a charge, that's an electron.
Mhm.
Beta plus has a charge, that's a positron.
Mhm.
Proton has a charge.
Mhm.
Neutron, photon, and that neutrino, they don't have charges.
Okay, I see.
But neutron doesn't have a charge, but has mass.
Right.
So we would write 0 mass, -1, 0 mass, +1. Mass is 1 and charge is 1.
Okay.
And there was one more alpha particle, that is nucleus of helium. Yeah, but technically, you don't really need, well,
So it would be
this is how it is used on the exam.
okay. So
With a symbol that represents that element, not just the alpha, beta, gamma, you know.
okay, but would we be given if it like the mass and the charge exponent and subscript?
For standard particles like these, usually not.
Okay. So we just have to know what the masses and the charges are for each
Well,
one.
the mass is on the equation sheet. The charge is what we should know.
But when we're doing like the conservation of mass thing, since a beta plus has 0 charge, we would add 0, right?
beta plus doesn't have this charge. Beta plus has elementary charge.
But it has zero mass, right?
No, there's mass number and there's mass, two different things. You kind of confuse these two things. There's mass number. The mass number is zero. There is mass. The mass is not zero. The mass is equal to 0.000585, whatever.
Okay, I see. Thank you for that clarification. Okay, so the equation is done. So then to solve for the energy release, I would do.
Yeah, let's just write it again. Electron and this 8, -1, 0, 15, 15, 7, and the rest is not important. So you need to calculate this mass, total nuclear, and you need to calculate this mass, total nuclear.
So for the left side, I would do the mass of an electron plus the atomic mass of oxygen, but subtract out the mass of electrons from that value.
Yes, so this would have been this plus atomic mass, which is, I would say, 15.
Okay.
That's normally standard.
Mhm.
Minus 8 electron masses.
Okay. And then for the right side, it's just 15 minus 7 times the mass of an electron.
Yes, exactly.
Subtract that from mass before.
And that's gonna give you delta M. That should give you, I believe, 2 electron masses, right? 15 minus 15 minus 8 minus 8 plus 7 plus 7. Oh, in this case, you probably need more accurate values.
Yeah, it's roughly 2.75.
Well, again, it's a WebAssign. This is how we would do it on the exam.
Right, yeah. No, yeah, I definitely agree with that. Would you be able to just outline all of the different radioactive equations that we have, like decay equations? Because I know we got beta plus, beta minus, and then we have now electron capture. And sometimes it's confusing for me. The atomic number always remains the same, right? Like it's always, or sorry, not, yeah, atomic number. Like that 15 would always be the same in every type of decay
Well,
equation.
if you've got beta plus or minus, that does not change atomic number. Yeah, because if you plus, doesn't matter on which side, minus, doesn't matter what kind of a particle. It does not have, this doesn't affect atomic mass number.
Okay,
It affects the charge, of course,
right.
but doesn't affect atomic mass number. But it carries mass.
Yes.
Mass is not zero. See, atomic mass number is zero. Mass is not zero for this particular particle.
Right.
Because if you have a nucleons and you multiply by roughly a mass of a proton, because it's actually lighter than neutron, this is an approximation for the atomic mass in kilograms. Atomic. And this mass is about 2,000 of the mass of a single proton. And this is not a single, this is 8 times more. So the mass is much, much less than the atomic mass or nuclear mass or a nuclear mass. So that's why this number is 0. But the mass itself is not, because the difference delta m depends on those decimals. Those decimals matter.
Right. So the only time that atomic number would be altered is if we were dealing with a proton or a neutron, because all other particles have an atomic number of 0.
No, alpha
Or-
particle also could alternate a
Yeah.
proton, a neutron, alpha. Well, theoretically, you could just collide two different nuclei. You could collide the potassium and oxygen. Why not?
Right.
So I'm not sure why you're trying to memorize each individual case. If there is a general rule, I would go with a general rule. A general rule is write a particle. You need to know
Mhm.
the values and use those values accordingly.
Yeah, I also need to memorize the exponent and subscript of each particle, like beta, proton, neutron, alpha.
Well, beta has a name, an electron, or an anti-electron.
Mhm.
And if you know this name, and we've used this name many, many times, you should know everything about this particle. Beta is, well, outdated term when people really didn't know yet if, if that's an electron or something else.
So an electron has no atomic number, but a proton does have a atomic number of 1, correct?
Yes, a proton is about 2,000 times more
Right.
massive. A nucleus is composed of protons and neutrons. You cannot set mass of a proton to 0
Right.
because it will make the whole mass of a whole nucleus 0.
Yes. Right. Okay. I see. Okay. That makes sense now. And then for that same problem set, can you tell me if question 10 is relevant to exam material?
No, I was answering that very question just before you called. And,
Oh, I'll just wait for your post then.
no, I finished. 10 is not. 11, 12, 13, theoretically, yes.
Yeah, I was able to solve those. I just wasn't sure about 10.
No, we didn't talk about that
Mm-hmm.
part. Yeah, so, no.
I see. Okay. Thank you so much. Those are all my questions.
Okay, you're welcome. Thank you.
Here.
Bye. Hello. Someone else joined? Yes, go ahead.
I just have a question. I have two questions actually. I have one about homework 3, problem set 4, question number 3.
Just a second. Homework. Okay, close this. Close this homework. What is my here? Close homework 3. Part which?
Part 4,
Part 4. Problem number
3.
3. So you got radioactive decay. And what does this mean? Let's take a copy. It's easier for me to read everything and write everything at the same time. So, come on. You got different numbers. So
Okay.
doesn't really matter at this point. You've got a sample of radioactive material which has a certain number of radioactive nuclei. How many do you have in your problem?
512 times 10 to the 10.
Okay, same. And the mass of your sample?
370.
370 grams. And you know that half-life is
1
equal
hour.
to 1 hour. That's the same. After how many hours?
5.
5 hours. Okay. Question is how many decays or how many remain? We have to read very carefully. So how many remain? All right. What law do you have to use?
I don't know what it's called, but I think it's where you multiply the number of total radioactive nuclei.
Well, if it's a radioactive element, you should use the law of radioactive decay.
Okay. That
And
one.
we have two different forms, mathematical forms for that law. Or because we have half-life, and because we should be able to recognize the power of 2, these two hints tell us we should use that law. Now, did you have a chance to look at the equation sheet number 3?
Yes, I did.
So the equation sheet number 3 has power of tens, so power of 2. So 512 is 2 to what power?
The 9.
So remember in the class, did you watch the lecture?
I did.
So we've got, well, I did it backwards. I'm not sure how it's on the equation sheet. 2 to the first is 2, 2 to the second is 4, third is 8, 16, 32, 64, 128, 256, and finally 512. What do they mean? They mean that if you wait exactly this time, your number of radioactive elements drops exactly to, well, on average, to a half of the initial value. That's why we call it a half-life. You wait one half-life, you get left one half of the initial. You wait another half-life, you get left one half of the initial for that interval, which is 1/2 squared. And you can wait longer and longer and longer every time. It decreases in a half. So if you start from 512 and you wait 1 hour, how many left?
You have 256.
256 left. Then you wait 1 more hour. Then you wait 1 more. Then you wait 1 more. 1 more. 1 more. Now, after 4 hours, or in your case, 5 hours, so 1, 2, 3, 4, 5. We don't need this. So, how many will left?
32. Or, sorry, wait. 16.
16. This is how we count it. Now, of course, we also should be able to calculate it mathematically. This will be equal to 512 times 10 to the 10th times 2 to this power, which is mathematically identical to this. So, oh, sorry, 512. So 512 tenth divided by 2. So you need to wait 5 hours, and half-life is 1 hour. 512 divided by 2 to the 5th. So you need to calculate this, and that will be the answer.
Okay. That's the way I did it, and then once I inputted it into WebAssign, it said I was wrong, so I'm a little bit confused.
I don't know. 512 over 5 hours, 1 hour, 32. 32. $16 again.
Okay, wait, I think I know, but I think I didn't see the times 10 to the 10th, so I put it in as 1.6 times 10 to 11.
Oh, well, yeah. You have to enter the answer that WebAssign wants from you.
Okay, yeah, okay. Sorry, okay.
That's okay.
Yeah. Okay, that makes a lot more sense now. Okay, thank you. I also have one more question from the homework set 2.
Okay.
I think I'm just like overall I'm having a hard time conceptualizing what value of M to use when we're having like when we're dealing with films.
Well, the answer is you have to try different values of M one after another and find the one that gives the answer that fits the requirement. That's it. There's never a specific value of M beforehand ad hoc that you have to use for sure. You have to try all of them and see which will give you the answer.
Okay. So it's more of like a trial and error process. There's no way of like kind of telling more from the problem itself.
It's not trial and error, it's trial and checking. You have to check. For example, I know there's a problem that requires the answer to be in a visible spectrum.
Mm-hmm.
So you have to try M equals 1. If that will give you the answer in the visible spectrum, you're done. If it gives you an answer outside of the visible spectrum, that means M1 doesn't work and you need to try in the next one.
Okay.
Do you have a specific problem in mind you would want to discuss?
I think that was number 6.
Number 6, okay,
talking.
all right, number 6. New one. Number 6. Ooh. Okay, so suppose we have a thin layer on glass. So we have glass 1.6, and this is N2 1.38, and we've got air 1, and the wavelength, and this wavelength in vacuum or air and you have to set it to condition for the minimum intensity. So 2t plus, there is a phase change here,
Mm-hmm.
and there is a phase change here.
Mm-hmm.
So they cancel each other. And that should be equal to 2m minus 1 times the half of a wavelength in the film. And what are you looking for? Thinnest T. Times wavelength in the film, 2 and 2 divided by 4. This is your equation. Now we have to start trying different m's. M equals 1, m equals 2. If you want to, start it from 0. It doesn't make sense, but it still works because it's not going to give you anything reasonable. So try it. Try m equals 1. Okay, 0. Try m equals 0. What does it give you?
If n equals 0, it equals to a negative number.
A negative number. So can
You
it
can't
be a
prove it.
negative number?
Mm-hmm.
No, it's not. It's
No.
thickness. So m equals 0 doesn't work. What about m equals 1?
That does give you a number, a positive number.
A positive number, and that will be the answer, I believe.
Okay.
Because there is no requirement in this particular problem. There is no. Oh no, it is. Oh no, it is already given to you. Yes, so it is in the middle of the visible spectrum. Yes, so you're all set. You just calculate wherever it is. That will be the thinnest, not the only one, because m equals 2 and m equals 3 also will provide you the same result, but they will give you thicker layers.
Okay. So I just have a question. So like, say that we have to find a range within a visible range. Will that range be given on the exam? So, because I think I've been like looking it up online. Or is that something we have to memorize?
Um, I'm not sure if you need to memorize it or it will be given yet, but it's really simple. It's between about 400 and 700.
Okay. Okay. Thank you so much.
Of course.
Thank you.
No
Have a good day.
questions? Okay, bye. Someone else? Anybody else there? No. Okay. In that case, I'm going to continue checking P. That's P. That's so let me close this. Oh, I left it. when we need to use the mass of an electron, we cannot use the mass of the proton for that. When the particle is an electron, we need to use the mass of that particle of an electron, and when we need to use the mass of an electron, we cannot use the mass of a proton for that. Oops. Да, чтоб тебя. What the meter producing is 1/3. All right, then we're, oh. Over, we are